So what we've talked about so far is this idea of just how we do nuclear equations, what makes up our nucleus and how that can change. We looked at the way of radioactivity this past week and how those pieces worked together. And then this week, we're going to look at what's actually happening with the energy that goes along with that. And so this goes along with the theory of relativity and looking at the idea of E equals mc squared. What does that mean? So I'm gonna go back and forth. Well, I will in a minute. So what we're looking at is that the energy that we have is due to, it's a change in mass. So technically there should be a little delta there. We write it like this way anyways. A change in mass times the speed of light squared. And so what you're looking at is teeny tiny changes in mass. What we know about what we know about the way that this works is, here's the thing. In chemistry, we talk about the whole idea of conservation of mass. And we say, if you're going to have a reaction of some sort, when you take your stuff, your reactants, and you put them all in the system, the mass of the system doesn't change. Only the rearrangements and then whatever you get, whether you get heat from that, whether you get change in color, whether whatever happens, you have your change in your chemical combinations, but the mass stays consistent, large scale. This gets us into this idea that when you break it down to teeny tiny pieces, and you take your mass of a proton and the mass of a neutron, and you put those together in the nucleus, you no longer have a conservation of mass, because the understanding would be, well, you have all these little parts, you're going to put those parts really tight together, and you're still going to have the same mass, they're just stuck together. But what was found experimentally was that when you had all those parts and you put them together into the nucleus, the mass wasn't as big. And so that's where the mass energy equivalence started to look at, of saying, well, what happens? And here's where it gets goofy. The idea is that the mass actually turns into energy, and that energy is used to bind the nucleus together, creating a strong force. So there's a lot just conceptually to get our brains around, because it goes against other things that we have, that we're familiar with. So when we look at radioactive decay, you have this spontaneous nuclear reaction. And we have, let's say we have a radium atom that is, that decays into an alpha particle and a radon atom. There is less mass after that, or with that reaction, than you would expect. And so the idea is that there's energy that's being released with that. And so when we start looking at these teeny tiny amounts, we have this idea that mass and energy can be equivalent and can go from one to the next. Again, conceptually, we're still sort of scientifically, as a whole, we're in that observing and predicting ability, a little bit with the controlling. This is where we're able to get nuclear energy. But we're not super far along in what we're able to do here. So let's talk about some different pieces. We're going to use something called the Unified Atomic Mass Unit. It's represented with a small u. 1 u is equal to 1/12 of the mass of a carbon-12 atom. And so 1 u is always going to be 1.661 times 10 to the negative 27th kilograms. And it says here that it can readily be shown using E equals mc squared that 931 mega electron volts has the mass of 1 unit. And so readily being shown is a little bit of a stretch. I'm going to go to my board here and just kind of walk you through what happens with that. So again, we're looking at this idea of mass and energy and how they can go back and forth. And so if we use the idea of E equals mc squared, and we take this mass of our single unit, we're going to talk about everything we're going to do from here on out is going to be talked about in reference to units and in reference to mega electron volts. And so as we're moving forward with this, just keep in mind that this is the basis of it, but we're going to kind of use some more practical numbers with what we're doing and moving forward. So when we say E equals mc squared and we use the mass that we have for the equivalence of 1 unit, we can say E is equal to 1.661 times 10 to the negative 27th kilograms. And what we're going to do here is only going to get an approximation. It'll be a little bit off from the 931 because I'm not using every single sig fig that exists. The 931 uses every single sig fig that exists. So what we have here, we have that, and then we have the speed of light. And so just for the sake of, usually we use 3 times 10 to the 8th. I'm going to use as many sig figs as I can without getting super obnoxious here. I'm going to use 299,792,458 meters per second. So this is our speed of light. I'll put that in there, sorry. Meters per second, and we're going to square that. Well, when we square this, we get an energy of 1.492832. Big, huge, long decimal 352 times 10 to the 10th, and that ends up being joules. Still not quite into our mega electron volts, but we know that we can get from joules into electron volts by saying that we'll multiply by 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. So joules will cancel out. We'll take this number here divided by this. Again, this is rounded, so we're not at every sig fig that we could have possible. So we'll take this divided by that, and we end up with an energy in electron volts. When we do this, again, everything is not, all sig figs are not present, so it's just going to be an approximation. We have 933,020,220. And that's in electron volts. Well, the use that we'll have most of the time is mega electron volts, and mega is times 10 to the 6th. So if I bring this 3, 4, 5, 6 decimal places over, we have 933 mega electron volts based on our our rounded estimate. And the more significant figures you bring in, the closer you get to being to that 931 mega electron volts. So we have to keep this in mind, because from here on out, we're not going to be looking specifically at E equals mc squared. So that's there. It gives us the basis for what we're going to do, but we'll be focusing on using units and using mega electron volts. So just kind of keep that in mind. I'm going to leave this here if you want to take a quick screenshot of it, and then we're going to go back to the slideshow that we have. All right, I'm going to go back here. Da-da-da. All right, so E equals mc squared helps us to see, based on what we just did here, that 931 mega electron volt is equivalent to the mass of 1 unit. And so that's kind of what we'll discuss in what's going on. So you have this tables of physical constants and masses of various atomic particles, and we'll have a table of that. That is going to, and I'll show you that before we go, that is in the back of your Holt book. It's on some pages that have purple. And so we have, this is the implication of E equals mc squared is that any reaction producing an appreciable mass decrease is a possible source for energy. And so we're going to look at how this works within the larger whole. There's this idea of mass defect and binding energy. And so what happens is, if you have, I'm going to go back to my board. Let me see what's next here. So if you have, in general, if you have your protons and your neutrons, so this idea of mass defect. Again, when we talk about chemistry, we're talking about the idea of whatever your parts are and whatever the whole is, the mass stays consistent. But when we look at the particles with the build of our nucleus, mass defects occur because the mass of your protons plus the mass of your neutrons is not equal to the mass of the nucleus. And what happens here, the mass of the nucleus you've lost mass in the process. And so because of that non-conforming to what we know about conservation of mass, it's looked at that change in mass turns into the binding energy of your nucleus. And so, again, we've talked about this idea that when we know about charges, if you've got a whole bunch of like charges within the same space, they're going to repel each other. So if you have protons, you have all these protons within the similar space, within that really tight space of the nucleus. If we're just talking about charges, well, all those protons would repel each other, and the ability to have a nucleus wouldn't even be there. And so this binding energy is what's happening with our strong force holding the nucleus together. And because you have this mass defect, this difference in mass from the parts to the whole goes from mass into energy in order to hold that nucleus together. On the flip side, when you release some of the particles, there's also energy that goes with that. So when you have, and that energy is in the form of radiation. It's carried either in the way of motion. So if you release an alpha particle, you have that energy that goes along with it in the way of motion, in the way of, if you have a gamma ray that's released, in the way of electromagnetic waves. And so these pieces together help us to see what's happening within the nucleus and then how we can use that to our benefit. Go back to here for a moment. And there we go. And so if we look at what this is set up here, it says that the second point, this is explained as being due to the binding energy of the nucleons together into a nucleus. And the mass defect represents the energy which would be released in forming the nucleus from its component particles. So you have your mass defect, that's the difference between the parts in the whole, and then that energy equivalent is called your binding energy. On the flip side, it would also be the energy needed to split the nucleus into its individual nuclei. So to separate all of it, you would have to have something that would overcome that energy in order to pull it all apart. So what we can look at is, and we'll do some of this, it says the binding energy derived in smaller manner from other nuclides is found to increase the mass of the nucleon as mass nucleon number increases. So for neon, it ends up being 160 mega electron volts. So essentially, the more stuff you have, the more binding energy you need. But we're also going to focus on this idea of binding energy per nucleon. And I'm going to show you a graph in a minute. So obviously, as you add more particles, you need more energy to hold that together, and so that graph would go up. It's helpful, but it's not going to give us much information. What does give us information is this idea of binding energy per nucleon. And when we talk about stability and the amount of energy that you can get from each piece, you can have you'll look at this graph and kind of see what you can do with that. So it says the next graph shows how this quantity varies with mass number, and in most cases it's about 8 mega electron volts. So this graph, this will be another one that you'll need to be able to reproduce a sketch of. And I want to talk about the different pieces of here. On the horizontal axis, you have your nucleon number. And your nucleon number is, oh, what just happened? I do not need to restart that now. try this again. Sorry about that. Your nucleon number is your number that is your protons plus your neutrons, that top number when you're looking at your at the way that we have it written. And so you can see that goes up 100, 200, and it goes up to, you know, your total number of nucleons that can be present. And then up the vertical axis, you have your binding energy per nucleon. One thing to keep in mind that when you reproduce this graph, it cannot just be your binding energy. This is not a graph of just your binding energy. That graph would continue to increase as you add more nucleons. This is your binding energy per nucleon. So if you take your total binding energy and distribute it and divide it by your number of nucleons, this is the graph that you get. And it's a measurement in mega electron volts. If you can see that 8 line, that's about where most of them start to hover around. The ones that are at that 8.5 type space is where you have really stable nucleus. Because what's happening is you have a lot of energy for each nucleon. So holding it together, you have a lot of energy. To pull it apart, you would need to add in a lot of energy to get that apart. And so those are the ones that aren't going to be messed with very much because you have such a strong binding energy. However, you've got two parts on here where it starts to be below. If you look closer over to the left and you have hydrogen, helium, lithium, those end up having a really small amount of binding energy per nucleon. And that's where we're actually going to have nuclear fusion that can occur. If you go to the other edge, down by like uranium and that general area, and it labels it on here that all nuclei beyond this point are unstable with bismuth there. If you're in that area, you still have a decent amount of binding energy per nucleon, but not as much as the ones that are stable. And so what happens with those is you have different particles that can be released by decay. They can also fairly easily go through the artificial transmutation process to be able to control what's happening. And with that, you can have energy that's released. And so what we're going to do is we're going to focus on this binding energy per nucleon graph. Like I said, you will need to be, and we'll add to it as time goes on, but you will need to be able to reproduce this and understand generally what's going on with it. And it'll make a little more sense with some other practice that we're going to look at. This is just what I was just talking about. So let's talk about what this looks like. So this is the idea of what happens with, so this one is an alpha decay. And so when we're dealing with alpha decay, you're starting, in this case, we have a thorium-228, and it's decaying by alpha emission. And so you have radium-224, and you have your alpha particle that's there. So if you look at the mass of the thorium-228 unit nucleus, it is specifically, again, this is a one specific nucleus. So we're not talking about average masses. We're talking about a specific one. And we have 227.9729 units. We will keep sig figs all over the place. At the very end, we'll round them, and that's about it. And so you'll have this. And so, but if you take that nucleus of thorium, and then you look at the particles that have been emitted, you have your 223.97189 for radium-224, and then your alpha particle is 4.00151. If you add those up, you only have that number there, 227.9340 units. It is less than the mass of your thorium nucleus. So you have lost mass. There's a mass defect there. It's not what was there before. That mass difference is really, really tiny. The 0.00589 units. Remember, 1 unit is like 10 to the negative 27th kilogram. So again, we're talking about these teeny tiny masses. However, if you look at that conversion into energy, if you take that 0.00589 times 931.5 mega electron volts, you end up with 5.49 mega electron volts being released in each alpha decay, mostly in kinetic energy. The radium nucleus does recoil a little bit because of momentum. This one doesn't indicate anything with gamma, but if there is a gamma ray being released as well, it would also go within that electromagnetic wave. And so in this situation where we're looking at decay, the parts of decay to the whole of decay, there's a mass defect there, and you have that energy that's being released. We can do that same thing with beta decay and look at that situation. And we can look at our areas of fission and fusion on here. So I'm going to kind of jump through that piece. Beta decay is going to work the same way as alpha decay. You're just looking at each of the particles that are there, and then the antineutrino has no mass associated with it. Fission means splitting up, and so when you have a fission reaction, it's going to happen where your nucleus is larger than larger than 200 nucleons. And other situations that can go along with it. So that area that we talked about before is fission. The area, we'll talk about fission fusion a different time. The area over here is fusion in that general area right there. And then your most stable, the one that has the highest binding energy per nucleon, is your iron there at iron 56. So again, another point to recognize when you're looking at this diagram is that your most stable one. So area of, I went the wrong way. Fission is down there. Fusion is right here. And again, I just talked about sort of with radioactive decay, how that energy is released. We'll get into the fission and fusion and that energy a little bit later. But the thing that I want to look at here is this idea of, I thought I had a different example on here, binding energy per nucleon and how we get to that. And so I'm going to take an example. I'm going to show you where so if you go to your Holt book, I'm going to pull that up here real quick. You go to your Holt physics book, maybe, and you go way to the back. I mean, like, we are in the appendices. Come on, farther, farther. Oh, and so you get to these pages that have purple on them. maybe. And this is your, where did they go? Well, let's try this. Appendix G and 874. So on page 874 is where you're going for this. Here we go. All right. So these pages, it's page 874 of the text. It's page 8. What is it? I don't know. 874, 892 of your PDF. And you get these pages, and it goes on for pages. It has every element that's there, and it has many of the isotopes. It does not have every isotope, but it has many of them. And so let's take, my favorite number is 27, so we're going to go with cobalt. And I'm going to just write down some information on cobalt here. Cobalt, we're going to do cobalt 59. Cobalt 59 has a mass of 58.933198 units. So make sure we have that cobalt 58.9933198. Yes. Okay. So here's what happens with that. Cobalt has 27 protons, and cobalt has 59 minus 27 is 32 neutrons. And so if you go to the inside cover, you can also use the data book. Oh, oh, I don't have that. Shoot. Let me do one more thing. That's what I need. Okay, so if you go to the data book, it has in your constants page, I jumped over, it has down here, it has electron rest mass, proton rest mass, and neutron rest mass. It has it in kilograms, units, and mega electron volts. And so for a proton rest mass is always going to be 1.007276 units. Neutron rest mass is always going to be 1.008665 units. And so what happens is, if we have these masses, we would take the mass of a proton, we'd have 27 protons, and we would have the mass of the neutron, we have 32 neutrons, and we're going to add those up. So if we take in our calculator and say, well, 27 times 1.007276 units plus 32 times 1.008665 units, we end up with this number, 59.47332. Again, you're gonna keep significance like forever until the end. So this is how many units. These are our parts. If I just had a bunch of protons, if I had 27 protons and 32 neutrons, I end up with this much mass. However, if we look at the mass of the actual nucleus, we have 58.933198. That's less. So what we're going to do here is we'll subtract to get our mass defect. So we're going to take away 58.933198 units. Again, whole lot of significance. Usually we like to round to some number of sig figs. Here, everything's significant until the very end, and I'll show you that when we get there. So we're going to subtract these two numbers. So I'm going to go minus 58.933198, and I'm going to get just not a huge number, 0.540534 units. This number here is my mass defect. That's the difference. That's what's saying, like, okay, well, there should be that, or there should be this, sorry, because of my parts. There's not. There's only this. This is my mass defect. So that's the difference from parts to the whole. That is what is being assumed then as our shift into energy. And so you're going to take this. Remember that we have that 1 unit is equal to 931.5 mega electron volts. And if you look back at your sheet, this is also in here, that you have a unified atomic mass unit is this many kilograms. 931.5 mega electron volts per coulomb squared. That comes from the E equals mc squared part of it. And so this relevant, or this equivalence here, we can take this many units, and then we'll take this times 931.5 mega electron volts. So times 931.5 gives us 503.5 mega electron volts. At this point, because you have your 4 significant figures here for your mega electron volt conversion, that's where you'll bring this down to 4 sig figs for your final answer. So what this means is that in order to hold cobalt together at the nucleus, your 27 protons and 32 neutrons would normally have this mass. However, when it's held together, it's this mass, meaning that this many units of mass have been converted into energy. This number here is your binding energy. This is how much energy it takes to hold a single nucleus of cobalt together. Then, in order to get it to kind of look at that on that graph of binding energy per nucleon, then you would take this number, and depending on what the question asks, sometimes it just asks for binding energy. Cool, you stop there. If it asks for binding energy per nucleon, you would take your number of nucleons and you'd be dividing by that. And so you would say 503.5 divided by 59 nucleons. And that gives you 8.534. And the unit on this would be mega electron volts per nucleon. Mega electron volts per nucleon. Shoot, I didn't get it quite all on there. Here is, this is your binding energy per nucleon. So you're looking at this process of identifying the mass defect, using that mass defect to figure out the binding energy, and then again, if the question is asking, figuring out that binding energy per nucleon. And so when you're looking at it in the way of just a single nucleus, you can go through this process like I just did here. I'm going to move this down. Let's say 59, 27, cobalt. There you go. So now you can have it all on one page. So if you want to take a screenshot of that, you can. And again, you're looking at that mass defect. What's the difference in mass? That mass is going into energy. So how does that energy, how much energy do you have? And then that binding energy per nucleon. That is what we're looking at. And that's what we're paying attention to here. If we go back to the idea of alpha decay, and you will do some stuff with this. If we look at alpha decay, way back here, way back here. There we go. You're not looking at your protons and your neutrons. You're looking at the idea of your starting nuclei and then the two pieces that form after that. And so in this one, you're not looking at all your protons and neutrons that make up your thorium. You're looking at I had thorium, and then the parts that came after that were radium and your alpha particle. And there's a mass defect from the start to the hole there, and that's what's being released. So whether you're looking at binding energy per nucleon, that's what most of our stuff focuses on today, or you're looking at your release of nuclear radiation particle, either way, you're looking at the mass defect from the start to the finish, what's happening with that. Let's see if there's anything else I want to make sure. I think we got all that on there. When we're talking about fusion, we're going to get some other pieces that go along with that. It's just, I don't know. I love this. I just think it's fun. I know that's a lot of stuff. Any questions to start with? All right, before we go, we're going to do one more piece on this. So we're going to take off this. Do that, take off that. All right, anyone have a favorite element? Anybody?
Potassium.
Potassium, all right. We'll go with potassium. K is right here. We'll go with, let's do, the highest percentage of it is potassium 39. So we'll go potassium 39. And so with potassium 39, let's just write down what that is before I do this. We have 38.96. Do you all see where I'm looking for this number here? Atomic mass units is going to follow along right here. And so if I'm looking at potassium, potassium's right here. Potassium 39 is this number here. And so this is the one I'm going to go with. And then the number for that is 38.963708. This number here shows the percentage that's naturally found. So 93.2581% of potassium is going to be potassium 39. And then if it is radioactive, it gives you a half-life of what it is on the end here. So not every Not every nucleus is radioactive, but if it is, it'll give you that half-life. So what we can do with this is we can say, well, we have potassium 39, so we have 19 protons plus 20 neutrons. So we can take our 19 protons times, sorry, I moved that already. Our proton rest mass is 1.007276 units, plus our 20 neutrons, 1.008665 units, and we can get our, wrong thing again, sorry. We can take and figure out our total mass of the parts. So we take 19 times 1.007276 plus 20 times 1.008665. And over here you end up with 39.311544. Here's the deal. When we're using this many units and this many decimal places, there's always the room for error in there. And so if you're getting something that's not right, go back and double check. Make sure you didn't flip a 1 and a 5 or whatever that might be. It happens pretty frequently here. So this is what your parts are. You're going to subtract the whole, so 38.963708 units. Take that minus 963,708. And here we get 0.347836 units. That's our mass defect. I tighten that up. Sorry about that. So that's our mass defect. That's our mass defect here. It's the difference between the parts and the whole. Then we'll take that number times 931.5 mega electron volts. We'll take that times 931.5 mega electron volts, and we get 324.0 mega electron volts. This is our binding energy. And then if we want to take our if we want to get our binding energy per nucleon, we'd say 324.0 mega electron volts divided by 39 nucleons. Remember that nucleons are just going to be the protons and the neutrons that are in the nucleus. Take that divided by 39. We end up with 8.308 mega electron volts per nucleon. So while this ends up being a really goofy idea and a goofy process that we're going through, reality is the process is pretty straightforward. It's more of a conceptual leap of what's actually happening in that process. So if you want to screenshot that one, you're welcome to. I, again, didn't get it all the way on the page. And then we'll go back to what we're doing. So for the stuff that you're doing this week, and we're up on time here, the stuff you're doing this week, you're working through this process. You're getting good at the practical application of being able to determine the binding energy, the mass defect, the binding energy, and the binding energy per nucleon with what is happening here. And keeping in mind that this mass energy equivalence is what's happening and how we're getting that. To do that using E = mc² just takes a lot more steps. This is the practical application of being able to do that. So have fun. If anybody gives you anything this week, you can be like, well, I'm just talking about Einstein's mass energy equivalence this week. I'm really smart. And just like tell them that and walk away. So so I hope you kind of have fun with it. Again, not a lot of people actually know what's being talked about here, and so it's kind of fun to be looking at what's actually happening and then how to figure that out. So I'll be on for a couple more minutes if anyone has any other questions. Other than that, have an excellent week. Enjoy your weekend, and I will see you next week at an earlier time. So we'll see you later. Bye-bye.